Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today, as with most of my screencasts, we'll be discussing the reciprocal system, in particular, the reciprocal system Microcosmos database, the electric and magnetic properties layout. In previous screencasts, I've covered solid-state matter properties, interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility. So we're going to look at this today. So we'll click there. It'll take about 10 seconds to load because it's doing lots of calculations. I've already pre-selected iron as the element whose properties we're going to look at. While that's loading, let me just turn this off. Hold on. Okay, it's back. Okay, so it's here, so I don't even have to go through the astronomy layouts. We'll do that later. Okay, so the top line is the same as before. Iron is the element. Form number 1, atomic molecular weight is here, melting temperature is here, thermal factor is here, compressibility factors is here. This is only for compounds, so we'll skip that. Input temperature is given here. We have the density calculations and zone, and these are special factors for anisotropic and amorphic compounds, so we'll skip that. All right, so now we're in here. This is the TE mod factor. That's for elements only. In this case, it's 5. TE means it's a modified electrical displacement unit. Okay, now for the properties. Remember, all these calculations are ab initio. You want the details, get my paper, which is in my magnum opus, the Existence and Interactions, a Computational Treatise of the Reciprocal System, the True Theory of Everything. So be sure to get that before you get the database here. So all these calculations are ab initio, which means they're from theory only. So electrical resistivity, both for the molecular calculations and for the aggregate. And the units are given in this column here. So we have resistivity, then we have conductivity. We have resistance for thermal resistivity, which is a little bit different, can be different. Electron specific heat is calculated here, it's volts per Kelvin. Thermal resistivity is here. Thermal conductivity is here. And here we have the Yaw's regression coefficients A, B, C here. And that's to compare with, empirically. The regression equation matches pretty closely with the empirical numbers. But remember, the reciprocal system is purely theoretical. So that's just a way for us to compare things. The Lorentz number is here. Thermal power, which is the Seebeck coefficient, is here. Peltier coefficient, the Thomson coefficient, the Hall coefficient is here. Thermoelectric figure of merit is here. And so let's jump over now. So this is the electrical part. Let's go to the magnetic part. These ferromagnetic charges, we can have up to 3. And then here's the edge C, the K factor, NMR. This is the basically the residual amount. After you remove the magnetizing force, what remains after a while? It's 2 instead of 3. Let's see, what does it say? It's like the appropriate dipole length description at remanence. That's what the R means, remanence. So here's the saturation internal magnetic flux density at 0 K. It's in Tesla. So always read the tooltips. This is saturation, internal magnetic flux density, temperature, T. So this is at 0, this is at T. So notice the difference, it's down. And then here's that at remanence, internal magnetic flux density, temperature, T. This is the average relative permeability of the ferromagnet in the second quadrant of the hysteresis curve. That's at room temperature, incidentally. And here are the parameters for the hysteresis curve. Now, you'll have to look in the book Existence Interactions to get the details of all this. Here's the maximum external magnetic flux density in the hysteresis cycle. And this is the calculated external magnetic flux density at the coercivity part of the hysteresis cycle. Okay? This is the magnetic hysteresis energy loss. And this is the magnetic energy product. That's B times H. So there's no calculation here. Alright, so now this has to do with the refraction vibration factor. And then this is the wavelength of light incident to the medium. And here we have the average index of refraction over all crystal edges. Let's see, it's okay. First term of the relative permittivity, of course. K factors are here. Let's see if I can get a definition. And this is another factor in that equation. Now here, I don't calculate this, but I do calculate this for other elements and compounds: index refraction, electrical permittivity, electrical susceptibility, and you know, whether this is diamagnetic, paramagnetic, ferromagnetic. Obviously it's ferromagnetic for iron. And here we have the number of diamagnetic or paramagnetic charges, would be 3. And here we have fraction of maximum possible magnetic dipole moments. And here's the maximum dipole length description. It's got to be HC in this case. And this is the geometric coefficient for the magnetic dipole length. Okay, wow. Let's see, this is the atmospheric pressure. Okay, so in this case it's okay, this is at 1 million, so it's pretty high. So let's just change this out of just reduce it, change it back to 0.001. It's going to take time to load. So I have to be patient. You can see that there are many calculations going on here. Okay, I'm going to go back here. I'm going to go 0, 0, 0, 0, 0, 1. Okay, so now we're back to 1 atmosphere. And that'll change some of these resistance and thermal resistivity values. Again, just be patient. I do recommend that you get a Xeon computer to run the Microcosmos database, but it's you know, it will run fine on i7 or i9. It'll just be a little bit slower. All right. Well, I think that kind of wraps it up. Except, well, let's go here. There's Stern-Gerlach temperature of the vapor in that experiment. The number of magnetic charges on each rotational system of the atom in the Stern-Gerlach experiment, so I'm not going to bother with that right now. And here, we have the first value of the calculated Curie temperature. Let's see. The second is, and that's the observed value. So there's a little bit of difference there. All right. Well, that pretty much covers it today. I mean, this is pretty involved. Again, you're going to have to consult Basic Properties of Matter by Dewey B. Larson, and Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. All right. So, if you want the simplest possible treatment, if you're a newbie to the theory, then please obtain my work, The Unmysterious Universe. Has all the diagrams, figures, all the concepts, very little in the way of math. But if you do want all the math, then get, as I've said in my work, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. And of course, you should read all of Dewey B. Larson's works, particularly Basic Properties of Matter. Now, after that, I have these two database modules. This is the Microcosmos database, solid matter properties, liquid vapor, gas matter properties, cosmic elements, subatomic particles, and photon properties. Very complete. The Microcosmos database I've already covered in screencasts, and this includes the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, and voids. Has a great graphing program here, same with Microcosmos, so you can graph most of the properties. All right, well, I hope you study the reciprocal system, and thereby you'll be able to prove it for yourself. And thanks for your attention, as usual.